So what we're going to look at here in this section is double integrals, but in terms of polar coordinates. Because sometimes it will be easier to describe our region D in terms of polar coordinates. For example, if I have, well, let's just say it's a circle, a disk, might call it, like that. Well, in terms of x's and y's, there's different ways I could do it. I could say, well, if I do, well, let's do the y's here. So this is a circle, radius 2. What would be the equation? The equation would be x squared plus y squared equals 4, right? Okay, well, so it's not hard to get the equation there, but think about this. What about my limits of integration, if you will, if I'm integrating over that region? Well, if I do the y's first, I have to go from this curve down here, which that would be y equals negative the square root of 4 minus x squared. And then the top one would be y equals positive 4 minus x squared. So that's what the y's would go between. And of course the x's go from negative 2 to positive 2. So that's so it's not that I can't find them, but if you think about this double integral over D for some f of xy, I'm going to have x's go from negative 2 to 2. The y's go from negative square root of 4 minus x squared to positive 4 minus x squared. And depending upon what this is, I'm not even saying what that is, but if you think about it, if I'm plugging in these for y, when I get that integrated with respect to y, that's going to be probably a whole lot of square roots and a lot of mess. However, what we can do is instead use polar coordinates, because in polar coordinates this is much easier to describe, because we're talking about a circle. Remember, in polar you need r's and thetas, and so my r's, since it's a nice lovely little circle radius 2, don't the r's range from 0 to 2? Well, let's do the thetas, I guess, first, because the thetas go from, I can go from theta equals 0 all the way around, so I go to theta 0 to 2 pi, and then the r's would go from 0 to 2. That's going to be a whole lot nicer limits of integration than these are. Okay, so that's one reason to do this. However, this integral, please note, the integral over d f of xy dA does not equal just straightforward, just change those up. Unfortunately, that's not quite that easy. You have to get your function in terms of r and theta a little different way, and then but here's the thing. We know in terms of polar coordinates what x equals, right? It's r cosine theta. And then the y equals r sine theta. And so we just use those conversions in my fxy. And then you also might use the x squared plus y squared. What would, because here's what we're talking about. We're talking about this x, any x comma y. So to get there, that's r. And so these just come out of the triangle, right? The x is r, that's theta. It's r cosine theta, and y would be r sine theta. And so x squared plus y squared equals r squared, or r equals the square root. Yeah. So those conversions can be helpful when you're converting to f of x, y. Now the other thing is this dA. That one's not, like I said, it's not just a straightforward dA turns into dr d theta, because when we were just using Cartesian coordinates, dA was dx dy or dy dx. But unfortunately, it doesn't turn out to be dA does not equal dr d theta. Here's why. If you take a look at, let's say I've just got two nice polar equations here, and so this one is, I think they call this one H1 R. Sorry, H1 theta. R1 equals H1 theta. And this would be R2. So we've got R's in terms of thetas for our nice little functions there. So anyway, if we go from theta equals alpha to beta, we're talking about this region in here. Okay. All right. So here's what the conversion. You know, in Cartesian, we divided up that into nice little rectangles, but when we divide it up in polar coordinates, we don't quite get rectangles. We get these little pieces, kind of curved. Yeah. All right. So we get not quite rectangles. Okay. It's something like that. Let's orient it more like it is. Okay. So we get these little pieces there. All right, well, you'll note here that it's not quite a rectangle, but it is. So dA would be, since dA is kind of rectangular, dA is approximately equal to the area of that, or let's call it delta A. We'll talk about dA in a second. All right, so the change in area, that rectangular area we've been talking about, is approximately equal to the area of that piece. Well, if we think of it as almost a rectangle, then this right here is what? It's the change in the theta, right? Because we go from, we're changing R. Changing R. This right here has to do with the change of theta, but that's more of an arc. And remember how you get arc length? You take the angle times, we have that right there. That arc length is R times theta, right? Or R, and that's theta. R times theta. All right, well, in this case, what we've got is my R to here would be, call it Ri, inner radius, times the angle I sweep out is just the change in theta. And then this one out here would be R. Okay. Now, so it's a little bigger. But, you know, I've really drawn this bigger than we really want it because we want smaller and smaller and smaller increments of that, right? And so if I take it where, you know, we're small enough where we can say that Ri and R0 are approximately the same and call that R, then this area here is approximately, and it's not rectangular, but smaller and smaller. Think smaller and smaller. It gets more and more rectangular. And so it'd be this times this. So R, using R for Ri, times delta R, delta theta. Okay? So if we do small enough, then we get dA, you know, dA and delta A. We've talked about the relationship amongst differentials and changes in y, or in this case a, they're approximately equal, but if you get smaller and smaller, they are equal. Just might as well say they are equal. R dr d theta. Okay. So dA turns out to be not dr d theta, dA equals R dr d theta. Okay. All right, so with all that in mind, this in mind, that in mind, here's what the integral over d f of x, y, dA, converted to polar coordinates is. First of all, we'll talk about the limits in a second. First of all, we're going to change from x and y to r's and theta, so x is r cosine theta, y is r sine theta. dA, well, what was dA equal? It was r dr d theta. Okay, and it is usually set up that way. We do the r's first. Okay, and so we do the r's. Well, again, here's the picture. R equals h1 theta. R equals h2 theta. And so I go from the r, as far as the r's go, I'll go from h1 theta to h2 theta, right? And then my thetas go from alpha to beta is what they usually refer to that as. Okay. So the main thing is, yeah, for x's, you do r cosine theta, or y is equal r sine theta, or you can use sometimes the x squared plus y squared equals r squared thing. But note here, there is an extra r that we throw in with my dr d theta. Okay. So let's do a couple of these. All right. That's okay. All right, so let's evaluate the integral over d of 2xy dA, where d is the region in quadrant 1. Between circles of radius 2 and 5, centered at the origin. Okay, so draw region D here. Quadrant 1, so we've got radius 2 and radius 5 circles. And so I want to do the quadrant 1 thing. So it's just that that part. That's my D. Yeah, so that is much easier to describe in polar than it is in XYs, because you got some things there. So anyway, all right. So let's change this integral to polar. And so in polar, first of all, we change the 2xy to polar, r theta. So what would that be? X is r cosine theta. Y is r sine theta. And then dA is r dr d theta. All right, then our limits, r goes from 2 to 5. Okay, so my radius, yeah, it goes from 2 to 5 nicely. And then the thetas, 0 to pi over 2. Okay. So what have I got? Combining the r's there, I've got 0 to pi over 2, 2 to 5, 2r cubed, cosine theta, sine theta, dr d theta. So it's not going to be hard to do the r's there, right? Let's see. All right, so r to the cube, so it'll be r to the fourth. Yeah, so 1/2 r to the fourth. Yeah, 2 to 5. Let's see, 1/2. So we've got 625, 5 to the 4th, minus 2 to the 4th, 16, so that's 609 times 1/2. Now, we could do this integral a lot of different ways. Here's one way, though. One way to do it is with, you could do substitution. However, one other suggestion here is remember that the sine of 2 theta is equal to 2 sine theta cosine theta, right? One of our trig identities. And so sine theta over 2 equals sine theta cosine theta. So, yeah, what I've got here is if I change that over to that, just to remind you of something we've done in the past, here we've got, so this is sine 2 theta over 2, or 1/2 sine of 2 theta. So you've got 609 over 4 times sine of 2 theta, and then to evaluate it, remember our double angle for, oh wait, no, that one's just U substitution, isn't it? So either way, I don't know if it's any easier. Yeah. So du is 2d theta, d over 2 and d theta. So, yeah, we've got the sine of u, 609 over 4. Sine of u, so that'd be, what, negative cosine of u? Which is 2 theta, and then divide by 2 there. And we're going from 0 to pi over 2. So this is negative 609 over 8 times, you do the cosine of 2 times pi over 2, so that would be the cosine of pi, minus cosine of 0. And so you get negative 609 over 8. Cosine of pi, negative 1, minus 1, cosine of 0. So it's negative 609 over 8 times negative 2. Yeah. So that's positive 609 over 4. Okay. All right.